Now let's look at question number 1A. The question reads, the standard enthalpies of formation for NO and NO2 are positive 90.37 kilojoule per mole and positive 33.80 kilojoule per mole respectively. The first question is define standard enthalpy of formation. So the enthalpy of formation is the heat change, meaning it can be both endothermic and exothermic, when 1 mole of a compound is formed, and that compound is formed from its elements in their stable states. Because this is the standard enthalpy of formation, it must be at 25 degrees Celsius and 1 atm. The next question reads, by referring to 1A1, explain why the standard enthalpy of formation for elements is 0. So the standard enthalpy of formation for elements like oxygen, O2, in the gaseous state is 0. This is also true for other elements like nitrogen gas or Cl2 and Br2. At standard conditions of 25 degrees Celsius and 1 atm, oxygen already exists as a diatomic molecule in the gaseous state. So there is no heat change involved for the formation of O2 gas because it is already present in this state. So this is what we can write as our answer. Next, we are asked to write the thermochemical equations to show the formation of NO, nitrogen monoxide, and NO2, nitrogen dioxide. Based on the definition for the enthalpy of formation, we want to form NO gas as the product. It is formed from its elements. So that will be nitrogen and oxygen, and nitrogen exists as N2 gas and oxygen exists as O2 gas. Because we want to form 1 mole of NO, this has to be 1/2 and this also has to be half. So the value of the enthalpy of formation for NO is given in the question, which is positive 90.37 kilojoule per mole. And we do the same for the enthalpy of formation of NO2. So this will be the product. It is formed from elements nitrogen and also oxygen gas. 1 mole of nitrogen dioxide, 1 mole of NO2. So that will be 1/2 N2. And the value for the enthalpy of formation is given in the question, which is positive 33.80 kilojoule. The next question is we are asked to determine the enthalpy change of the following reaction, and we must use an energy cycle diagram. We have the two equations that we wrote in the previous question. So we will use both of these equations in the energy cycle diagram. We can start from any of the known equation. Let's start with this equation. So this produces NO2, but our target equation produces 2NO2. So let's multiply everything with 2 because it is a positive reaction, a positive delta H. We will go up, so the reactant will be N2 gas and 2O2 gas to produce NO2 gas. So this is delta H3, so it's twice the value. So that is 2 times positive 33.80 kilojoule. So we've used this equation. The other equation that we know the value of also uses the same reactant of N2 and O2, but it has a larger value than this value. So again, because the target equation uses 2NO, so we're going to multiply everything in this equation by 2 with 2. So that is N2 because it's half N2 multiplied by 2, and then we need 1 O2. So that gives us our product NO. So 2NO and also 1 extra oxygen gas because we're only using 1 for this equation. So this is delta H2. So it's twice the value. And our target equation is 2NO, which is over here, and 1O2 to produce 2NO2. So this is actually 2NO2. So this is our target equation. Okay, so to figure out the value of delta H1, we will use Hess's law, which states that when reactants are converted into products, the enthalpy change is the same whether the reaction takes place in one step or a series of steps. So let's choose the reactants. We can either choose this or this as the reactant. So let's say we choose this one as the reactant and this will be the product. The one step will be from here to here, and the series of steps will be from here to here. So that will be twice the value of delta H2 that we use equals to 2 delta H3 because we're going in the opposite direction, that will be negative delta H1. So we'll substitute value, that is 2 positive 90.37 kilojoule equals to 2 positive 33.80 kilojoule minus delta H1. So after pressing the calculator, that gives the enthalpy change of the target equation, which is negative 113.14 and the unit is in kilojoules. Now we will look at question 1b. The question reads, an aqueous solution of lead 2 nitrate was electrolyzed using a current of 2.0 ampere for 30.0 minutes. Determine the volume of gas evolved at the anode at room temperature. From Faraday's first law of electrolysis, we know that the amount of product formed at the electrode will be proportional to the amount of charge that is supplied to the cell. So we can start off the question by calculating the amount of charge. The equation that we will use is Q equals to IT. So we can substitute the value of the current and the value of time, and according to the definition, for 1 ampere the time must be in seconds, so we will convert minutes to seconds. So after substituting in values, we get the value of charge. So now we have to determine what is the gas that will form at the anode. From the question, we know that we have an electrolyte of aqueous solution of lead 2 nitrate. We want to look at the anode. The anode will be the electrode that is connected to the positive terminal of the power supply. So the positive electrode will attract negative ions, which is the nitrate ion NO3 minus, and also water molecule. The question does not state whether the electrode used is an inert or active electrode, but we know that if an active electrode is used, which will be lead solid, it will be oxidized into Pb2 plus ions, which is not a gas. Therefore, the anode is an inert electrode. So now we have two candidates for oxidation, which is NO3 minus and H2O. Let's start by considering the oxidation number of nitrogen in NO3 minus. The oxidation number of nitrogen in NO3 minus is positive 5, which is its maximum oxidation number. Because the valence electrons of nitrogen is 5 and nitrogen has used all of those valence electrons to form bonds with the 3 oxygen. So nitrogen do not have nitrogen in NO3 minus has no more valence electrons to be donated. So what will undergo oxidation is water. So water will oxidize into oxygen gas. We will balance the oxidation equation by starting off with oxygen. So there's 2 oxygen here, so that has to be 2 water, and then balance the hydrogen atoms by adding H plus. So that is 4H plus. And then we balance the charge where this is 0 and this has a charge of positive 4. So that involves 4 electrons. From the equation, we can see that 4 moles of electrons, which carries a charge of 4 Faraday, will produce 1 mole of oxygen gas. 1 mole of electron carries a charge of 1 Faraday, and 1 Faraday is equal to 96,500 coulomb. So 4 moles of electron carries a charge of 4 times 96,500 coulomb, which produce 1 mole of oxygen gas. This is the actual charge that is involved in the electrolysis. Substitute the actual amount of charge that is involved in the electrolysis to figure out the amount in mole of oxygen gas. The volume of gas is collected at room temperature. So at room condition of 25 degrees Celsius and a pressure of 1 atm, 1 mole of any gas occupies a volume of 24.0 liters. So this is the actual amount of oxygen gas produced. So then we can figure out the volume of oxygen gas, or we can also use ideal gas equation of PV equals to nRT.